We looked at local maximums and local minimums. You might ask the question, well, what is the biggest of all the maximums and the smallest of all the minimums? Well, those we're going to call global maximums and global minimums, and we'll be looking for those too. Let me say, just as I did before, that I will use the word global in this class. Sometimes you'll see the word absolute being used by other books. It means exactly the same thing. You also saw me use local in place of relative before. Now I'm using global in place of absolute. So my words will be local and global, but they do mean the same thing as relative and absolute. What we want to do now is consider a function, let's say f of x, and let's take some interval I that's contained in the domain of f, so f is defined totally on I. And finally, let's take some point in that interval I. Now I want to define what a global maximum and a global minimum is. And it's a pretty easy idea. It's just the biggest and the smallest values that the function takes on. So the definition is the following. F, this function, has a global maximum, at the point x naught if, when you compute f of x naught, you are bigger than or equal to every other f of x for all the x's in the interval we're looking at. If we want to say that f as a global minimum at x naught, then that will happen if when we compute f of x naught, it's not bigger than or equal to everything, it's less than or equal to every other f of x for all the x's in that region I. And just as we did with local extrema, we will say here global extrema if we want to talk about, well, or extremum if we want to talk about either one of these without specifying which one we want to talk about. And just let me give you a few pictures so you see what we're looking at here. If you have a curve something like this would be a global minimum. It is the lowest place on the curve. If you have a curve like I drew once before, this up here would be a global maximum. It's not only a local maximum, but it's the largest of all the local maximums. Likewise, this would be a global minimum down here. Now, don't be seduced into thinking there are always going to be a global max and min. Let me give you some examples here. Here is a nice function, just a straight line segment, but it's missing the two endpoints. This function has no global maximum or global minimum. If there were to be a global maximum in it, would be those very points that have been omitted. So this curve, although it looks like it has a top point and a bottom point, it doesn't. There's nothing there, and so there's no global max and global min. Another more dramatic way of looking at that situation is if you have a curve like, say, the tangent function in one of its regions. This function goes down to infinity and up to infinity, so it has also no global max and no global min. Now you could say that the global max and global min are infinity, but that wouldn't be correct because global max and global min are actual heights, finite heights of the curve, and this does not have a finite height or a finite depth. So this is a case where there's none. So you won't always get global maximums and minimums, but when you do, you want to know how to find them, and we will do that next. Let's examine now the nuts and bolts of actually finding these global extrema. Global extrema, first of all, on closed intervals. And the main tool here is this theorem. This theorem is well known. We won't prove it, but we'll talk about it at length, and you should memorize it. This is called the extreme value theorem. And it is an example of what we call in mathematics an existence theorem. It tells you something is always going to be there. Here is what it says. This is really very handy. If f is continuous, So we want a nice continuous function on a closed interval AB. Now let me stop and make sure that you understand that both hypotheses are necessary here. If you have only one and not the other, the conclusion that we're going to write down is not guaranteed. You must have a continuous function on a closed interval. If you have that situation, which we often do, then f has both a global maximum, so it has an actual highest point on its curve, and a global maximum, a global minimum, actual lowest point on its curve on that interval AB. This is guaranteed. As long as you meet these two hypotheses, continuous function, closed interval. If the function is not continuous, this may not happen. If the function is continuous but it's an open interval, this may not happen. You're only guaranteed if you have both of these at the same time. So this is an example of what I called an existence theorem, because it says a global minimum and a global minimum and a global maximum exist. It doesn't tell you how to find them, doesn't tell you where they are, just tells you that they're there. So our next question is, well, now that I know they exist, where are they? Well, here's a further theorem which will add to that. Suppose we have f, and f has a global extremum, which could be a global maximum or a global minimum, on an interval. And this interval is on an interval AB, which is an open interval, you notice. Suppose it has a global extremum on an interval that is open. Then that extremum must occur at a critical point of f. And this makes perfectly good sense. Think about what we had before. If we had an open interval where there was a extremum of some kind, a local extremum, a global extremum, among other things, is certainly a local extremum. It's just the locality is the entire interval. So a global extremum is a local extremum, and we know that local extremums on open intervals must occur at critical points. We already had that theorem before. So all this says is that the global fall into the same category as local. They're just special locals. So with those two theorems, we can summarize a procedure. If you have the situation where you have a continuous function, this is absolutely essential again, you have a continuous function on a closed interval, then here is what you can do to find those extrema. First of all, you know from the first extreme value theorem that f has both global extrema. So they exist, and you know that they're there, and you want to be able to find them. Where do they occur? Well, these occur at either A and B, which are the endpoints of the interval, or if they do not appear at the endpoints, then they appear in the open interval AB, and we just had a theorem that told us what to do about that, or where f prime is equal to 0 or f prime doesn't exist, which is just me writing out the definition of critical points. So this is the critical point definition. And I'll write that down here. Critical points of f. So if f is continuous on a closed interval, first of all, you know you're guaranteed to have both global extrema. There's going to be a global maximum and there's going to be a global minimum. Where are they? They can occur either at endpoints or they can occur at critical points. So endpoints or critical points are the ones you want to look at. That limits the number of things you have to check. And critical points, as you know, are where the derivative is 0 or where the derivative doesn't exist. So how do we actually locate those points? Well, here's the procedure. What you want to do is, first of all, find all the critical points. That usually takes a bit of time, so you go ahead and do that first. Find all the critical points of f that are in the interval in question, the closed interval AB. Then you evaluate f, the function, at these points, these critical points, and also evaluate it at A and B, which are the two endpoints of the interval. So you have this collection of critical points and the endpoints. You evaluate the function at all of them. One of those will be the global maximum and one will be the global minimum. The largest value that you get in this process will be the global maximum. And the smallest value that you get will be the global minimum. It's just that simple. So if you just compute f of A, f of B for the endpoints, and then f of every one of the critical points, then you just look at the collection of numbers you have. The largest number is the global max, and the smallest number is the global min. That's it. Let me show you this with an example. Here is the function. F of x, it's a polynomial. 2x cubed minus 15x squared plus 36x. And let's take it on the closed interval 1 to 5. The question is, find all global extrema. So find all the points where the functional value is as large as possible or as small as possible on this closed interval. Here is the solution. I will need to find the critical points and the endpoints. The endpoints are given to me, so I just read them off. The critical points I'll have to find by finding the first derivative. So I do my first derivative as I've done so many times before. 6x squared minus 30x plus 36. This nicely cleans up to 6 times x minus 2 times x minus 3. Factors nicely. That means I have my critical points now. My critical points are where this would be 0, which is x equal 2 or x equals 3. So now I have two critical points and two endpoints. I just take my original function and evaluate that function at these four numbers. And then I pick out the largest value and the smallest value. That's it. So I compute here f of 1 and f of 5 because those are the endpoints of the given closed interval. Then I compute f of 2 and f of 3 because those are the critical points. Now, if you'll allow me to leave the arithmetic to you, f of 1 turns out to be 23, f of 5 turns out to be 55, f of 2 is 28, and f of 3 is 27. So I can see by looking at these four numbers that the first one's the smallest, which means the global min is equal to 23 at x equal 1, which means the global min will occur above or below the point x equal 1. 55 is the largest number, so that is the global maximum value. And the global max will be 55, and that will occur at x equal 5. So it turns out in this problem, the global min is at the left endpoint and the global max is at the right endpoint. Now, it doesn't always happen that way. Very often it's in the middle, but not in this one. And if we actually look at a quick sketch of the graph on 1 to 5, it has a picture that looks something like this, where this is a height of 55, which gives us our global max, and this is a height of 23, which gives us our global min for this particular function. So that should be something that you'll find very easy to do as you do problems on your own. What if we want to find global extrema on open intervals? Well, the problems there are that we have to be a little more careful about what we're talking about. Let me write this down. Even for continuous functions, which are our favorite functions, even for continuous functions, if you go onto open intervals, so the endpoints are not included, global extrema are not guaranteed to exist. They are there sometimes and not there other times. So what can happen? Well, we're going to draw a few pictures to give you an idea, but what happens is that you simply have to check all the critical points to see what you've got. You're not guaranteed that there will even be an answer when you're done with that. What can happen? First of all, let's look at the largest possible open interval. That's the interval from minus infinity to infinity. That's all the real numbers. What can happen? Well, you can have pictures that look something like this. Perhaps you'll have a curve that looks like this. It goes up in both directions forever, and so this would be a case where it has no global maximum. It grows without bound in both directions. Well, if that works that way, it can also work the other way. You might have a curve like this that has no global minimum. And I'll actually show you some curves like this in a moment. And then you can also have curves that roughly do this sort of thing. They either go up to the right, coming from the far left up to the right, or go the other direction. And in this case, they have neither. No global maximums, no global minimums. That can happen if a function is defined on the entire real number line. And the classic example of such functions are our old friends, the polynomial functions. They are defined on minus infinity to infinity, of course. And that is going to show us that there are four different cases for a given polynomial p of x, which I'll write out because I need to refer to some things here. If I have a n x to the n plus all the way down to a1x plus a naught, that will be my generic polynomial, and I'll assume that a n here is not 0, so we're not starting a polynomial that doesn't have that degree. So this is a degree n polynomial. What can happen with polynomials? Well, there are four cases. Let me divide my page up here into four parts, and I'll show you the four cases. If n is even, if the degree is even, like squared or fourth power and so on, and the leading coefficient a sub n is positive, then the curve is going to look something like this. It'll be something here in the middle, and then it will go up to the right in both directions. I like to think of this as your arms being lifted up in both directions. Something's happening in here, I don't know what it is, but when I go far out to the left and right, it goes up forever. An example of such a function, of course, is our old friend y equals x squared, the parabola that goes up. This is an example of a function with no global maximum. No point is the highest point the function reaches. If n is even again, and this time a sub n, the leading coefficient here, is less than 0, then all it does is flip this over. So the function does something in here, but on the far ends it goes down. So y equals minus x squared is a perfect example. And this is an example of no global minimum. There is no point on the curve, which is the lowest point. If n is an odd power and the leading coefficient is positive, then what happens is on the left you've got a function that is negative, and so down this way, and on the right it goes up to plus infinity in that direction. So it might be doing something else in the middle. I don't care. I'm looking at the two ends. Y equal x cubed is a perfect example. This is a case that has neither a global maximum, so there's no highest point, and no global minimum. And finally, if you have n odd, the degree is odd, and a sub n is negative, the leading coefficient is negative, then all you get is the reverse of this, flipped across the y-axis, and y equal minus x cubed is a perfect example of that, and this is another case of neither. So these things all happen. Polynomials are limited to these four cases, but these can happen with other functions too. Now, this was for the largest possible open interval. What if you have an open interval that's finite in extent, like an open interval from a to b? again, what can happen? Remember, too, that we're talking about a continuous function, so there are no breaks. There are not going to be any asymptotes within this open interval. However, there may be asymptotes at the points A and B because they're not in the interval. And that's exactly what happens here to cause you not to have global maximums and minimums. So the answer is, what happens? Vertical asymptotes at an endpoint. Now I'm going to draw these with vertical asymptotes at each endpoint, but of course it could only be at one, and give you more examples. So if this is A and this is B, and the function is defined in the open interval, it's possible that the function is asymptotic on each end. So here is a case where this function will have no global maximum. And it is on an open interval that is not the entire real number line. And these asymptotes force it to go up to infinity and have no largest point, so it has no global maximum. And now you can see what I'm going to do with the rest of these. If this is A and B, it's possible you have a curve like this, which is asymptotic on each side, so it would have no global minimum. And then you can have the other cases we saw on the other page. If you have asymptotes at one or both of these sides, you might have a function like this, which will have neither a global maximum or a global minimum, and it could go the other direction too. So this exactly mimics what was on the other page, except that it's bound on this finite interval, and the asymptotes are what make it happen. So this would be neither. So all of these kinds of things can happen on open intervals. There may be no global maxima or minima, or there may be one but not the other. Let's do an example to illustrate some of this. Suppose f of x is 1 over x squared minus x. And algebraically, a good idea would be to rewrite this so you have x squared minus x to the minus 1 power. And if you notice that factors, let's pull that out too. We never know when this is going to be useful. X times x minus 1 all to the minus 1 power. Let f of x be this function on the open interval 0, 1 only. Find any global extrema. Solution. Well, the first thing is there are no endpoints. The endpoints 0 and 1 are not part of this interval. So there are no endpoints to check. Where else can global extrema occur? Well, they occur at exactly the same places that local extrema occur, which are critical points of the function in the interval. So we check critical points. This function is going to be defined everywhere except, you can see from here, because x times x minus 1 is the same as this, that it's not going to be defined at 0 and it's not going to be defined at 1, which is not a problem since those aren't in the interval. So within the interval, this function is defined everywhere. And let's see what happens when we look at its derivative. The derivative, let's see, I will choose this middle form. I think this is easiest to work with. So using the middle form, I get minus 1 times x squared minus x to the minus 2 power times the derivative of the inside, which is 2x minus 1. That simplifies to 1 minus 2x over x times x minus 1 squared on the bottom. This is going to be 0 for x equals 1/2. That's where the top is 0. That's easy to check. And realize, of course, that it doesn't exist for x equals 0 or 1. Those would be where the denominator is 0. But we don't have to worry about these. These are not in the domain. Not in the domain of the function f, so they're certainly not going to be in the domain of a derived function from f. So we have just this one critical point. So we can calculate the functional value at the critical point. That's our lone critical point. And if we do that, we get what? 1 over 1/2 squared minus 1/2, which turns out to be minus 4. So this is our only candidate for a global max or min. But which is it? Is it a global max or a global min? Or possibly neither? So the question we ask ourselves is, which is it? Well, let's go ahead and use one of the tests we know. Let's use, say, the first derivative test. Since we already have the first derivative lying around, let's go ahead and use it. And recall that the first derivative from the other page is 1 minus 2x, and it's over something that is positive. And the reason I'm writing it this way is because the first derivative test only requires that I find out where the first derivative is positive or negative. So since the bottom here is always positive in the interval 0, 1, the open interval, I just need to figure out what's happening on the top. So with that in mind, I can now say for x in the interval from 0 to 1/2, which is the left-hand side to the left of 1/2, f prime of x, let's see, if I'm to the left of 1/2, numbers like 1/4, if I put that in here, I'm going to get a positive number as my first derivative. So the first derivative is positive, and so that means the original function is increasing on the left. Then for x in 1/2 to 1, the right-hand side to the right of 1/2, what is f prime of x? Well, if I go to the right of 1/2 and pick a number like, say, 3/4, and I put that in here, I have 1 minus 6/4, well, that's negative. So the first derivative is negative, which means the original function is decreasing on the right. So if you go up on the left and down on the right, what happens in the middle? Well, so f has a local, hence global, maximum of minus 4, the value we calculated here, at the value x equals 1/2. And if we actually look at the graph of this function, this is what we end up with. If this is, this should have been dotted in here, this is 1, this is an asymptote, then you'll see that the function graph between 0 and 1 actually looks like this, and here at minus 4 is the local maximum, which is in fact the global maximum of the curve. That last example we looked at brought up an interesting point. What if you only have one local extremum in an open interval? Doesn't that force it to be a global extremum? Well, it turns out that's true. And let's make sure we realize that we're talking continually about continuous functions. So the continuity of the function f forces this to hold, this business of a single local extremum that happens, that must be forced to be a global extremum. The continuity of f is going to force this to hold. And the theorem goes like this. Suppose we have a function f and the function f is continuous, and it has exactly one local extremum. At some point, say, let's call it x0 in an interval. And I'm not specifying what kind of interval, whether it's closed, open, or not. If at that local extremum, if it happens to be a local minimum, so if f has a local minimum at x0, then f at x0 is not only a local minimum height, it is the global minimum on all of I. So if you have a local minimum in an interval, and it's the only local extremum that's in there, then it's going to have to be the global minimum. There's no choice. And I'll show you why with a picture in just a moment. And likewise, of course, if f has a local maximum at some point x naught, then it's guaranteed that f of x naught is the global maximum. If there's only one, it has to be the biggest or the smallest. And it all happens because the function's continuous. Here's the idea. Suppose we have this situation. Suppose we have an interval here, I. And it could be closed, it could be open, it doesn't matter. Here's a point x naught in here. Now above this point, let's just, for the sake of argument, suppose I have a local maximum. So on some locality, which I've represented by writing it as a curve that goes around this point a little bit, in this locality, this is the highest point. Now suppose, and let's put it at an endpoint just for fun. There, as an endpoint, is a point on this curve that is higher than this point. Suppose this is a global maximum over here. How can we get from here to here? Remember, this is a continuous function. To get from here to here, I have to be able to draw a line without lifting up my pen. There are no breaks. The only way I can get from here to here is if I do something like that. Well, look what I've just done. I have added a new local extremum. This one happens to be a local minimum, but I had assumed that there was only one local extremum in here. So if I am not a global maximum here, then to get to the global maximum and keep the function continuous, I'd have to create another local extremum, and that violates the conditions. So there can only be one, and this one must be the global. That's all there is to it. And we saw this. We saw this with the function we looked at previously. F of x equals 1 over x squared minus x. That was what we saw in the previous section. And that was on the interval 0, 1. And that's exactly what happened there. There was a local maximum, it was the only one, and turned out that was also the global maximum. So this can happen, and it's worth noticing, and sometimes it'll save you trouble. Rather than go hunting for a global maximum by some other means, if you have a local maximum, then you can, and it's the only one in an interval, then it must be the global one, and the story is over. Now for our final set of exercises involving the analysis of the graphs of functions. Suppose we take this function, f of x equals x minus 2 sine of x. We need some practice with the trig functions. On the closed interval from minus pi over 4 to, say, pi over 2. Find both global extrema. Now I know they exist because this function is continuous and this is a closed interval, so I know I have a global maximum and a global minimum. Your job now is to find both of them. As I said, this function is continuous on a closed interval, so we're guaranteed to get both a global maximum and a global minimum. Where might they occur? Well, they might occur at either one of the endpoints or at critical points. So, since the endpoints are right here in front of us, let's find out what the critical points are by finding the first derivative. So the first derivative of x minus 2 sine x is 1 minus 2 cosine x. When will this be 0? This will be 0 for when 1 minus 2 cosine x equals 0, which means, let's see, cosine x would be equal to 1/2. Well, let's see, on this interval, I want to remember what the cosine is that has, what angle has cosine equal to 1/2. One way to do that is to remember these little triangles, which I always like to do. I remember the triangle that has pi over 6 in this corner, and the sine of that is 1 over 2, so opposite over hypotenuse, which makes this side over here square root of 3. This angle up here will have a cosine of adjacent over hypotenuse. So this angle, which is the angle pi over 3, has a cosine equal to 1/2. So this will only happen for x equal pi over 3, and I say it's only for pi over 3 because we're restricted to this interval. And in this interval, pi over 3 is the only angle that will fit in there. If you take pi over 3 and add and subtract a 2 pi, you can get other values where the cosine is equal to 1/2, but those would be outside this interval. So only x equal pi over 3 here. and this is a critical point. And that's our only critical point. So we have one critical point, pi over 3, and we have two endpoints. So what do? We take the function and we check out each one. F of minus pi over 4, f of pi over 2, those are the two endpoints. And finally the critical point, f of pi over 3. And we'll see which one's largest and which one's smallest. And the largest will be the global max and the smallest will be the global min. So f of minus pi over 4, I'm going to do a little bit of this to see how much trig you remember. Minus pi over 4 minus 2 times the sine of minus pi over 4. Now the sine's an odd function, so this minus sign inside comes out. And then the sine of pi over 4, well, if you draw the little triangle that goes along with that idea, a 1, 1 triangle with the square root of 2 here, both of these angles are pi over 4, then the sine is going to be the opposite 1 over the hypotenuse square root of 2. So this becomes minus pi over 4 plus 2 times 1 over the square root of 2. And that is approximately 0.63. For the second one with pi over 2, that's going to be pi over 2 minus 2 sine of pi over 2. Sine of pi over 2, of course, is 1. So this is pi over 2 minus 2. That turns out to be, separating these out a bit here, this is approximately minus 0.43. And finally, for pi over 3, we have pi over 3 minus 2 times the sine of pi over 3. Well, back in this picture, the sine would be the opposite over the hypotenuse. So that's going to be pi over 3 minus 2 times the square root of 3 over 2. And if you simplify this and approximate, you have minus 0.68 approximately. Which means that 0.63 is the global max. And minus 0.68 turns out to be the global min. And the global min will occur at pi over 3, and the global max will occur at the left endpoint minus pi over 4. And one thing that you might want to do at this point is graph this function on this interval and verify that these are in fact the global max and the global min. Let's try one more. Find the global extrema of the following. Now this is a little unusual because this is a piecewise defined function. Let's make it 4x minus 2 whenever x is less than 1, and x minus 2 times x minus 3 whenever x is greater than or equal to 1. And this is the general function, but we want to restrict it to a closed interval, 1/2 to 7/2. Now if this function is continuous, and you'll have to check that yourself, if this is continuous on the closed interval, then you're guaranteed a global max and a global min. If it's not continuous, who knows what might happen. So see what you can do in finding these two extrema. So we're looking for global extrema. Well, we have an interval, a closed interval, and provided this function is continuous, we would be guaranteed that there's a global extremum of both sorts, but we're not sure it's continuous without some checking. But let's go ahead and try out a few things that we can do. First of all, there are endpoints, so let's just note what those are. That's 1/2 and 7/2. Okay, x equals. Let us now look for critical points. And this would be where the first derivative is 0 or doesn't exist. Well, since this is broken up into different pieces, and we really haven't checked yet that it's continuous, though we will, for x less than 1, we have the form of the function at the top. The derivative would be equal to the derivative of 4x minus 2, which is 4. Well, that's never going to be 0. And so that is never going to give us a critical point. Okay. For x greater than or equal to 1, what does the derivative look like? Well, let's see. I don't want to take the derivative of this as it stands. Let me go ahead and multiply this out. It's a little easier if I do that. So it's x squared minus 5x plus 6. Now normally I like things factored, but in this case by multiplying it out I'll find it easier to take the derivative. The derivative is 2x minus 5. This will be 0 for, let's see, x should be equal to 5/2. So I do have one critical point I've discovered on the right side of 1. And let me note that for x equal 1, the derivative doesn't exist. Which of course is another way of saying there is a critical point there. And I'll show you why it doesn't exist. Because if you take the derivative on the left-hand side, as x approaches 1 from the left, the derivative on the left-hand side is always this 4. Now that's not going to be equal to minus 3, which is what you get if you take the limit of the derivative as x approaches 1 from the right-hand side. Because the derivative is this. If you approach 1, this becomes 2 minus 5, which is minus 3. So from the two sides you get two different numbers. So this derivative doesn't exist, which means 1 is another critical point. So 1 is another critical point. So I still haven't checked whether this function is continuous or not, because I really don't need to. All I know is that if I don't know that it's continuous, I'm not certain that I have a global maximum in. And yet I might be able to find it anyway. So let's go ahead and check, as we always do. So f at 1/2, that is one of the points to check. That's a left endpoint. F at 7/2 is the right endpoint. F at 5/2 was a critical point we found where the derivative was 0, a stationary point that is. And then f of 1 was a point where the derivative did not exist. If we put these back into the functions, 1/2 is less than 1. So that's the 4x minus 2 part of the function. So this is 4 times 1/2 minus 2. That's value of 0. For the 7/2 part, we're in the other part of the function, so it's 7/2 minus 2, 7/2 minus 3, that's 3/4. For 5/2, that's again bigger than 1, so that's 5/2 minus 2 times 5/2 minus 3, that's going to be minus 1/4. And 1 is right on the cusp. It is defined by the second form of the function. 1 minus 2, 1 minus 3, that's going to be equal to 2. Well, it certainly looks like minus 1/4 is the global minimum, and 2 is the global maximum. We weren't guaranteed that they existed because we don't know whether the function's continuous or not. Now, we could have checked that earlier, but it really doesn't make a lot of difference in our calculations. Now, finally, let's look at the graph. This is a standard piecewise function, and you should have some experience in graphing these. The breakpoint occurs at 1, and to the left of 1, the function is a straight line that passes through the x-axis here at 1/2, because we're only going from 1/2 to 7/2. So it is just that straight line. And then the other function is a parabola, of course, going as far as 7/2. And if you check it, it's easy to see that it's a parabola that looks like this. Passes through 2 and 3, goes here to a height of 3/4, and there is the depth of the parabola is minus 1/4 here. And that is the complete graph of this piecewise function, which breaks right here at 1. And you see that it is actually a filled hole here. It is open for the left-hand function, but it is filled by the right-hand function. So in fact, it is a continuous function, even though there's no derivative there, as we showed. So this is an example of a function, and there, look, there's the global maximum at the height of 2, and the global minimum is right under here, just as we predicted from above. So that was a little bit more interesting problem, and I hope you enjoyed it.